So let's continue our study of kinetics and let's look at it in terms of the integrated rate law. And this allows us to predict how much reactant there will be or how much product will be formed in a given time period. And now this is really super helpful for reactions that have a slow rate. All right, for example, we know that the half-life of carbon-14 is over 5,000 years. Well, a scientist isn't going to be around for 5,000 years to see how much of the carbon-14 remains. So how do we know that the half-life is 5,000 years? So what we can do is we can look at how much reactant there is or how much left or how much product has been formed, and then we can make some predictions based upon that experimental data that we were able to collect in the lab. So this is really helpful, especially for reactions that move at a slow pace. So let's look at the integrated rate law for the zero order. So if we were looking at it in terms of A, all right, this is the disappearance of reactants. I know these are reactants because of the negative. So my rate law, if it's a zero order, is K equals A to the zero, which cancels out, leaving me with just K. And then I can do some calculus. And when I do some calculus, I can rearrange the above formula to this. A final concentration minus the concentration of A initial equals negative KT. So the decomposition of ammonia gas is a zero order with rate constant of 3.4 times 10 to the 6 molar per second. If the initial concentration of ammonia gas is 0.0068 molar, what will be the concentration after 1,000 seconds? So here is my formula for this zero order. And now I'm going to simply plug in my values. I'm looking for my final concentration. I know my initial concentration. I know my rate, K, and I know my time. So I can simply solve, and I find that A, T, which is our final, is 0.0034 molar. So let's look at the integrated rate law for a first order reaction. And again, we're looking at it in terms of reactants because you see here we've got our negative symbol and rates are always positive. So when I write my rate order for reactant A to the first power, rate equals K, A to the first power, which is K, times the concentration of A, and I can do some calculus to come up with this formula for a first order reaction. So the natural log of my final concentration minus the natural log of my initial concentration equals negative KT. So let's do an example. The rate constant for the decomposition of cyclobutene C4H8 at 500 degrees Celsius is 9.2 times 10 to the negative third seconds to the minus 1. How long will it take for 0.02 molar sample to remain from the decomposition of 0.1 molar sample? So I've got my formula, and again, I've got my, in this case, we're looking for time, how long, so we're looking for T. So I have my final concentration, my initial concentration, and I'm taking the natural log of this, and I've plugged in my K value, all right, which was provided right there, our rate constant. Okay, 9.2 times 10 to the minus third. And when I plug this into my calculator, I get 164 seconds. I need you to pause this video, plug this into your calculator. Do you get that value? If not, you need to contact me so that we can work on using your calculator skills. We need to get those skills to being mastery. We don't just want We want them to be mastered. Let's just stop there. We want it mastered. So if you did not get 164 and you cannot figure out why, you need to contact me. Okay, friends? All right, let's look at the second order. So here we have, again, we're still looking at the reactants A. So rate equals Ka is the second order, so the concentration of A squared. And we can do some calculus to find our value or our formula, 1 over the final concentration minus 1 over the initial concentration equals Kt. So let's do this reaction of this butadiene gas, and it's going to react with itself in a second order. What is the concentration remaining after 10 minutes if the initial concentration is 0.2 molar and the rate constant is 5.76 times 10 to the minus 2 molar negative 1 minutes negative 1. All right, so we're going to use our formula that we found, 1 over concentration equals of the final concentration minus 1 over the initial concentration is going to equal Kt. So I'm just going to plug in my different values that were provided in the problem. Now we are looking for our final concentration here. So I knew my initial concentration. Here is my rate constant. Here is my time. So when I do this, I end up with 1 over concentration equals 5.56. I'm sorry, 5.576 molar to the negative 1. And then when I solve for A, I get 0.179 molar. Again, please plug this into your calculator. Pause this video. Make sure that you get this value. Now, if we wanted to go back, let's look at the graphs of these. So we've done some math. Let's look at the graph. Notice that the graph of a zero order is a straight line when I look at the concentration versus time. This is important. In our first order reaction, we had the natural log of the concentration. So our straight line, our linear, I shouldn't say straight, I should use the word linear. Let's use the appropriate terms here. My linear line here is the natural log of the concentration versus time. And for our second order, we had 1 over concentration. So you'll notice our linear line is the 1 over concentration as compared to time. So if we were to provide you with a graph, you would be able to determine if it was a zero order, a first order, or a second order based upon this y-axis, all right? If it's concentration versus time, that was a 0. The natural log is a first, and the 1 divided by concentration is a second, but you have to figure out which one is linear. All right, so the key here is looking at a linear line. So if it doesn't give you a linear line, it can't be that particular order. All right, most radioactive decay is a first order reaction. And the key here is the word most. All right, so for our purposes, we're really going to just stick to first order decay for the most part, okay? Our half-life is going to equal 0.693 divided by K, my rate constant, where the half-life, if you'll remember from honors chemistry, is the amount of time it takes for half of a sample to decay. Remember, decay is a continuous process, so it's happening continuously. However, we denote by how long it takes for half of the sample. All right, so our rate constant again is dependent on temperature. So temperature as temperature changes, so does half-life. All right, half-life is, when we graph it, an exponential decay. So the anti-cancer drug, and I'm not even going to try and pronounce that, all right, hydrolyzes in water, with a rate constant of 1.5 times 10 to the minus third minute to the minus 1 at a pH of 7 and 25 degrees Celsius. So this is all data we collected experimentally. Let's calculate the half-life for this particular drug under the conditions provided, a pH of 7 and 25 degrees Celsius. So my half-life equals 0.693 divided by K. Here's my rate constant, 1.5 times 10 to the minus third. So we're just going to simply plug that in, and we end up with a half-life of 462 minutes. So this has a half-life of 462 minutes, meaning half of that sample will decay in 462 minutes. Using the same question, let's look at another part B. If a freshly prepared solution has a concentration of 0.053 molar, what is the concentration after 5 half-lives? So you can use your half-life equation from your Math 3 if you would like to. That's perfectly fine. I don't do that. This is how I do it. I draw an arrow for each half-life. So if I have 5 half-lives, 1, 2, 3, 4, 5. So I draw 5 arrows. I've written down the concentration I started with, and now I know that the half-life is the time it takes for half of a sample to decay. So I'm going to divide 0.053 by 1/2, and that is 0.0265, which I divide in half again, and I divide 0.0133 in half, and then 0.00663 in half, and then 0.0031 in half. And here we go. This is my final concentration. All right.